Okay. Is it on?
Yeah.
Okay. Hello, everyone. I'm Dominik Szafranek. I'm the host of today's seminar. It is my pleasure to host here Vladimir Villegas. Little about his history. So he was doing bachelor, master, and PhD at the University of Philippines. In bachelor, he was doing quantum information, and during PhD, he switched to condensed matter physics. And after he graduated, he became an assistant professor at University of Santo Tomas, then switched to Mapua University, where he became associate professor. And today he will tell us about quantum thermodynamics and spin transport of open one-dimensional single-band Fermi-Hubbard systems. Floor is yours.
Okay. Thank you, Dr. Szafranek. Thank you, everyone. So first of all, I would like to thank the PCS IBS for having me here right now. And again, I'm Vladimir Villegas, and I'll be talking about the quantum thermodynamics and spin transport of open one-dimensional single-band Fermi-Hubbard systems. And well, here's a rough outline of my talk. But before we get too serious, let me just introduce myself. So as Dr. Szafranek has told that I graduated my undergrad, master's, and PhD from UP Diliman. During my undergrad, I was working on the Heisenberg XX model with Professor Eric Galapon. And during my doctorate, I was working with Professor Christine Villagonzalo on the Fermi-Hubbard model. And actually, I taught already for 3 universities, the first one being De La Salle University. The second is the University of Santo Tomas, and actually these 2 universities have something in common. They are both run by Catholic orders. This one is run by the Brothers of the Christian Schools, and this one is run by the Dominican Fathers. And now I switched to a non-sectarian university, which is Mapua University. I will introduce it later. And actually, before we get too serious, well, in fact, you sometimes want to trace who are the advisors of your advisor, and keep on tracing back. You might stumble upon some familiar names there. And just look at this one. There are 1, 2, 3, 4 Nobel Prize winners. Big shoes to fill in, right? What a pressure! Because we need to go further than the ones who came before us. I just hope that this one is the next Nobel Prize winner, right? So yeah, and even if you so quantum mechanics and statistical mechanics. So if you even see here, my roots even trace back to Heisenberg, and even it traces back all the way to Ludwig Boltzmann over there. So you know what's the pressure there. And for more introductions, well, before we get too serious, in fact, the country where I came from, the Philippines, is made up of 7,641 islands. It's called the Pearl of the Orient Seas, and it has a population of around 110 million people. And well, its capital, Manila, is located over there. And well, however, the most populous city is Quezon City, which is just beside it. But at the same time, there are a lot of islands, so you're very welcome to visit our country and even visit our very beautiful beaches, especially here in Palawan. Yeah. Actually, my hometown is a bit way up here. It's called the Ilocos region. This is the point where the Japanese started to invade the Philippines during the Second World War, whose end we are commemorating 80 years, whose end now turns 80 years this year. So it's been 8 years since the Second World War ended, and that actually the Filipinos speak around 130 to 195 native languages. Not necessarily that they know all of it, but like the ones here do not speak the same language as the ones here, and even the ones in this part don't even speak the same language as the ones in this part. These two might understand each other at some point because they have the same they have a same lingua franca, nonetheless. But there is the official language, Filipino, and then actually we were formerly colonized by Spain, United States, and even Japan. So if you see, even my name itself sounds, well, my first name sounds Russian, but my surname sounds more Spanish. And actually, the university that I work for right now is a private research-oriented, non-sectarian university, Mapua University. And was actually named by in honor of the founder, Don Tomas Mapua. And actually, Don Tomas Mapua has a registration number in the Philippines for his for his licensure as architect. 0000000000000001. So he's the first licensed person in the Philippines. And actually, he's a graduate of Cornell with Gonzalo Tivales, and they established it in 1925. So it's just been 100 years since Mapua was founded. And actually, because of the 100 years, just a few months ago, I need to dance with the other new faculty members. That's a tradition in the Philippines. We can talk more about it after this one. But, well, in 2000, it was turned over to a particular corporation, the Yushchenko Group of companies. The Yushchenko family actually handles things like banks and even insurance in the Philippines. And well, it attained its university status in 2017. So here are some notable alumni of Mapua, and actually these three are engineers. That's why they say that if you want to major in engineering in the Philippines, this is the university that you go to. But the physics program is also starting to thrive as well. So yeah, exciting times ahead. Now, let's first talk about, now let's get to the more serious part. And actually, what I'm going to talk about today is that of the open Fermi-Hubbard model. So what's the Fermi-Hubbard? Well, actually, this first applied for the case of optical lattices. And optical lattices are done in such a way that you have a dilute gas, let's say rubidium or even sodium, and then from that dilute gas, you're going to superpose lasers. And once you superpose lasers in 3 dimensions, you can align them in a certain crystalline formation. That's why optical lattice. And then actually, the more realistic picture of which is that those particles which are not trapped by the superposed lasers can act as a bath to that of your system. So, well, it is a type binding model, meaning that, well, for example, this spin-up particle can jump onto this site. And this spin-down particle can also jump onto this site, provided that there is no spin-up nor a spin-down particle. So, for example, this one can never jump going there, okay? Now, actually, and then, of course, since we have a thermal bath, then there should be a chemical potential with it. Now, after the chemical potential, what makes the Hubbard model Hubbard? So what makes it Hubbard is none other than the two-particle interaction. That is, well, for example, here, you have, for example, compare this site onto this one. What happens is that there is an additional energy because two particles are occupying it. Well, we are speaking of a fermionic system, so that it should be two particles can only occupy that site provided that they don't have the same spin. And in this case, spin up and spin down. So yeah, but however, as I've said, it's as I've told a while ago, it applies to optical lattice, but it also applies to other systems, just like spin 1 half cuprates and even spin 1 nickelates. Well, that's for the bosonic part. Now, As I've said, this is an open quantum system. And since open, well, we need to define the system, which is the optical lattice. We need to define the bath, which is the Fermi gas bath that we have, or rather the gas bath or the particles that were not trapped into the lattice. And we need to define the interaction in between them. So those are the three things that you have to have in order to define the total Hamiltonian of the system. So let's start with this lattice. Now, life is too simple, right? Let's complicate it. So you have here the tunneling term, wherein S of S here is the spin of your particles, which can either be spin up or spin down. And then L is the lattice site. So this one goes backward, and then the Hermitian conjugate would make it go forward. While on the other hand, this one is the chemical potential term. And well, as you see here, the chemical potential acts as if it is a single particle occupation energy. And then, well, let me skip some terms first. This one is the Hubbard term, which defines the on-site two-particle interaction. Now, let's add in more complications. Let this lattice interact with external electromagnetic fields that we can amplify or we can diminish. So let's start with, so first you have magnetic field. And when you have a magnetic field, it has a different count for the spin up and the spin down. Like call your Ising model just like that. And then if you subject it to an electric field, what happens is that the electric field can push or hinder your particles from going forward. And that's why the summation in this part is L plus 1 and then minus that of L. So this is the magnitude of your magnetic vector potential. This one is the magnitude of your electric scalar potential. And then let's add another two-particle interaction. So that two-particle interaction now exists in between the nearest neighboring sites. So how is that? Let's say that, for example, I'll just use this one. For example, you got a spin up here and a spin up at that one. So that's additional energy for those two particles. So that's just what I mean. But this one and this one, since they are not nearest neighbors, no additional energy for them. So this is the more general Hamiltonian for the lattice that we want to tackle. By the way, this one, some might ask, how about the spin orbit coupling and the other effects? Well, spin orbit coupling is not yet accounted for in this model. Okay, now, how about the bath? Well, for the Fermi gas bath, we do know that the fermions two fermions can occupy the same energy level provided they are of different spins. And well, once the ground level is occupied, they would keep on piling up. And that is why, well, let's make things a bit simpler this time, however, such that let's subject our bath onto a mean field approximation. And what's that? Well, only one energy level is accessible for the optical lattice. The rest, let's neglect them. So the things in the bath, or rather the particles in the bath, need to go down to that particular energy level in order to interact with the particles of the lattice. And then, well, S sub B here is the spin of the particles in the bath, which is also either up or down. And then, so if you subject the lattice to a particular gas bath, then what happens? Well, there will be an interaction in between your system and your bath in such a way that that interaction looks like as if they are Bogoliubov excitations. And that's why the interaction has a Hamiltonian of the form of equation number 4. Wherein, what do we have here? This is the density of your bath. This is the volume of your bath. And then this one tells the effects of the interaction of your bath particles and the lattice particles. That is, your bath particles allows your lattice particles to have an additional scattering length alpha sub I. So that just means that the interaction between the bath and the lattice particles give an additional energy onto your lattice particles themselves. So let's limit our study. Out of the generalizations that I presented a while ago, let's put on some limits onto this. First is that let's suppose that our lattice only has a single band. That is, it's just one energy level also up. And then, well, for the case of quantum thermodynamics, because I'm going to use later exact diagonalization, I would have to make use of the dimer. Because, if I go beyond the dimer, there would be more, the density matrix of the lattice would have more entries, would have more dimensions. That's why it will be harder, it will require more computing resources. And then let's suppose that this system is a half-filled system, meaning that, well, our chemical potential is always half of the two-particle on-site interaction. And, by the way, that two-particle interaction can either be positive or negative. If it's positive, it means that it's repulsive. If it's negative, it means an attractive. So, well, with that implication, it just means that if U is positive, then mu is also positive. It just means that the dispersion relation in our optical lattice is gapless. However, when U is negative, U is also negative. It just means that the dispersion relation in your optical lattice has a gap already. Now, and then let's suppose that our two-particle interaction among nearest neighbors will not be accounted for. So let's just set U sub E into 0. And then, as I've told a while ago, mean field path. And then let's just suppose that this factor a while ago is of this form, for simplicity's sake. Well, there will be no loss of generality with that because it's a constant that you can, actually these two are constants that you can randomly set. So yeah, those are the ingredients of our system. So this study will comprise two parts: quantum thermodynamics and even spin transport. So for quantum thermodynamics, I'm going to make use of exact diagonalization methods. And for spin transport, I'm going to make use of analytical methods. So let's first talk about what we want to learn about the quantum thermodynamics of the system. And the main one of the main parts of it, which comprised more than half of my dissertation way back in 2022, is magnetocaloric and electrocaloric effect. And what is that? Let's suppose that you have this system of a particular temperature T1, expose it onto an external magnetic field, and then it changes temperature. So that's what you call magnetocaloric effect. And at the same time, and similarly, if you expose that same system of temperature T1 onto an external electric field, it emerges with a different temperature. This is what we call the electrocaloric effect. Now, how do we make sure that the things that we are given that actually we are going to adjust in such a way that all the energies of the system would be in terms of the tunneling energy T later on? But how do we make sure that what we're really doing is sound, that what we're really doing is correct? Well, we will let in this subject, in this study, that T equals 1, but in fact, in experiments, T is equal to, well, this is your Planck's constant times 570 Hertz. And if, in fact, the first thing that you will, you have the board. The first thing that you will make use of for the, that you will make use of the tunneling energy later on is actually your temperature. So it will be K sub B times capital T is equal to T. So that if you compute for the temperature here, it's just T, small t all over Kb. So plug in plug in this one, and then plug in the value of your Boltzmann constant, you would get that actually the temperature that we're operating on is approximately equal to 30 nanokelvin. And actually, this temperature is the temperature on which your quantum heat engine and refrigerator experiments are being carried out at. So now, we have that concept. So what are the methods that we will make use of? Well, statistical mechanics. And if statistical mechanics are just, since this is a system and a bath, then the most appropriate thing to use is none other than the grand canonical partition function. And it's given by this equation. Notice that in this one, I did not spell out already minus mu times n because, well, the chemical potential term is already accounted for in the total Hamiltonian. And then again, K sub B is your Boltzmann constant and T is your temperature. So actually in statistical mechanics, right, once you have this grand canonical partition function, it's done for. Majority of the things in your system can be determined already, especially the average of any variable A, which is just computed as this. And what we're interested about are the thermal fluctuations of these properties later on. So once you, in fact, from this grand canonical partition function, right, you can derive your Landau free energy. And from the Landau free energy, you can get your entropy and even your heat capacity. So if you keep on taking all the derivatives, actually, you can simplify all those derivatives in this following form, in such a way that it would be a averages in terms of the Hamiltonian. And well, you see here the temperature dependencies of those variables. So let's give this, give a run of these results to produce some phase diagrams. And actually, for U is equal to 2T here. And let's shut the electric field off for a while. Here are some plots of your entropy and your heat capacity in terms of your magnetic vector potential and even the temperature. So let's go through them one by one. Okay, this plot first. Sometimes I and my advisor lovingly call this plot Batman. Anyone know why? Anyone?
Looks like a bat.
Yes, this one. So yeah, if you look at it sideways like that, there's Batman, right? So yeah, so why so what now? If it looks like Batman, well, actually these are lines for which your entropy are the same. For example, this one is the line for which the entropy is equal to 1.5 times Kb. So these are isoentropic lines, and those isoentropic lines would converge at a particular value of your magnetic vector potential, right? At t equals 0. So what are these degeneracy points? Actually, if you want to maximize the entropy, you want to, at t equals 0, you want to go there, right? And then let it evolve on the temperature. But more than that, what happens is that at low temperature, once you go from here, going up there, it will undergo a phase transition, particularly a singlet to triplet transition. Because right, if you recall your quantum since these are spinful particles, if you subject them onto stronger and stronger magnetic fields, what happens is that there will be a degeneracy among the particles. So let me use this. For example, you have your optical lattice here. Some particles, as I've told, half field. So some particles are spin up, some are spin down. Then let's subject it to a magnetic field that points this way. Once the magnetic field points this way, actually, the spin of particles will be influenced by that magnetic field, and they will now be pointing down. So there's a degeneracy among your among the states, right? So that's why singlet to triplet transition. Now, and then what about them? If you have this one, you can also look at it on the heat capacity. Yes, question?
Sorry, just to understand what you are doing here. So you have two spins in the Hamiltonian. Your
This is spin 1/2.
So no, the Hamiltonian. What is the dimension of your Hamiltonian?
What do you mean by dimension? Okay,
the
so
matrix that you are diagonalizing. What is the dimension of that?
okay. Since one side would be, let's go for from one side to the whole. So this one is actually 4x4 for one side because empty, one spin up, one spin down, singlet. See, well, when I mean singlet, I mean that there's a spin up and a spin down at the same time. So if you, since I'm considering only a dimer in for the quantum thermodynamics part, it would be 4 times 4. So 16 by 16 Hamiltonian for the lattice.
16 by 16 density matrix.
Density matrix, yeah.
And
even the Hamiltonian, yeah.
Your bath is mean field.
Is mean field, so it's only 4x4. So
could you go back to the expression of your bath once again?
This one.
Yeah, could you explain what did you mean by mean field once again?
Mean field means that only one energy level is accessible. The others neglect it because we assume that, well, all the particles in the bath need to go down onto this energy level so as to interact with the lattice particles.
Okay. So essentially then you have 4-dimensional Hamiltonian.
Yeah, actually 4 times 4, so 16 by 16 Hamiltonian for the lattice. And then, well, for the bath, since it's mean field, it's also 4 by, and only one level. So empty, spin up, spin down, singlet. So it's 4x4. So overall, 16 times 4. So it's going to actually 64. The total Hamiltonian is 64 by 64 in dimension.
And then now could you go back to the Batman figures that you were showing?
Yeah.
So are you going to talk about magnetocaloric effect and electrocaloric effect with this?
Yes, actually. Yeah.
So then I don't, because just before I don't know that much about these two effects.
Yeah.
But you just mentioned that you had some sort of temperature change, right?
Yeah.
And but you are working with some constant temperature or something. So
no. This is the temperature.
I see.
Yeah.
And H is magnetic field?
H is the magnetic vector potential.
I see.
So they're both magneto.
Yeah, this is a 3D plot actually.
So it's a okay. And these phases that you were talking about, these are just the phases of the Fermi-Hubbard, like the Hubbard model.
Yeah.
Mott insulator phase transition.
Yes, actually. Mott insulator is one application of the Hubbard model.
Yeah, but yeah, I mean it's a very small system, so probably those and you don't see the effect of your bath in some ways there because
actually this was compared with a particular publication with actually that was which served as a basis, this number one, but the study by Zhalovsky and Balcherzak. Actually, what happened when there was no bath for the case of Zhalovsky and Balcherzak is that for this particular region that they observed the Fermi-Hubbard model, there was only one transition point. But well, when the bath was added, there came two transition points. So that's the addition of the effect of the bath.
So could you explain what's interesting about it? I don't get the idea of this graph.
When with the absence of the bath, there's only one transition point. There's only one of this, which is a transition point.
From where to where?
This one is singlet. This one is a singlet part, and this one is triplet.
So in terms
So
of-
actually, they would start to flip it like that. Or rather, once you bridge this one, it would be inevitable that the spins in your system are going to go down like that, for example.
So for full-blown lattice, it will be a phase transition between Mott insulator and superfluid,
Yes.
which you are now calling singlet and triplet.
Yeah. Mm. Okay, thank you. Further questions so far? Okay, I'll proceed. Okay, so actually, these transition points also correspond to the points where, well, at that particular magnetic field, there is this hole on your heat capacity, the constant, well, this is a heat capacity at a constant volume. Yeah, so there's a comparison. And well, how are you going to make use of this? Actually, later on, I will explain how this can be useful on, well, making your quantum heat engines. And well, not only can you produce these kinds of figures when you modulate your external magnetic field, you can also do it when you modulate your external electric field. And in fact, you still get the Batman here. But well, if you compare it, this one has more transition points, right, compared to that of the electric field. For this span of the electric field values. So lesser transition points. But this one's instead, a while ago, what we're having is singlet to triplet transition, but this one is the reverse. It's a triplet to singlet transition instead, because the degeneracy is broken. Yes?
And why do you have a symmetry around T equals, like if you go back to the earlier picture,
yeah,
there is a symmetry around
T equals 0.
Whereas that is gone in the next figure, right?
Yes, actually, this one is operated when H is equal to 3P.
Okay.
And well, instead, what we modulate is the electric field. So there's no symmetry at electric field is equal to 0. Whereas this one, sorry, not that. Whereas this one, there was a symmetry when H equals 0.
So there's some symmetry at 3 or minus 3, or?
Sorry?
Is there some other symmetry point?
Well, the symmetry point seems to be somewhere here, but not really a very perfect symmetry for this one. Because if you see this part, if you trace it all the way back, none. Yeah, so that's what the electric...
Even with the bath, should you expect a symmetry?
Actually, these ones are with the bath.
No, so, that's why I wouldn't expect a symmetry in the earlier case.
Okay, yeah.
Why you have a symmetry there?
When there is no bath, actually, there was a symmetry when at E is equal to 0. But well, when bath was added, it shifted. What happened is that it shifted up there. Yeah. And then actually, just like a while ago, these transition points or these points of degeneracy also correspond to where you have these pools here in your chemical potential. If you're your heat capacity, I mean. So actually, this is applicable to quantum heat engines. And well, what's the difference first between your quantum heat engines and your classical heat engines? Well, if you we all do know about the PV diagrams of our classical heat engines. And for example, for Carnot, you got isothermal expansion first, then adiabatic expansion, then isothermal compression, and then adiabatic compression. But well, I'd rather use ST diagrams for this one. However, so instead of calling it adiabatic expansion, we can call it isoentropic expansion, which is this one. And the difference between a classical heat engine and a quantum heat engine is that, well, you got no adiabats for that one. So in fact, the isoentropic expansion also takes in some work compared to that of the classical heat engine.
Why is that? Why is that?
Why is that? It's part of the quantum. Even with a consistent entropy, well, work can be taken in during quantum processes.
But when you take adiabatic in quantum, it also means there is no exchange.
Actually, this is no longer adiabatic.
It's just
It's isoentropic, but not adiabatic
ice
anymore. Yeah, the same thing. Actually, the same thing happens when you have an auto heat cycle. But the thing is, for an auto heat cycle, there are no isothermal parts. Actually, so in fact, how do we make use of this one? In fact, we can use this by manipulating your external fields. So let's before I show that, let's try to look at it first. So isoentropic, isothermal, isoentropic, isothermal, isoentropic. So how do we do that? Well, sorry, I think I pressed the wrong button. No, okay. I think someone. Oops. How do we hide this one on tech help, please? Thank you. Okay, they're just experiencing some technical difficulties for the ones who are online.
Please go back to your Hamiltonian once again.
Okay, sure. This one.
Yeah. You are essentially working with, you don't have the last term, right? This
one, no. I set it to 0.
But you do have the E term.
Yes, yes. This one, yes, yes.
Could you explain that term? How is that electric?
This is the electric field. Electric field, charge. So this is the scalar potential.
Scalar potential, okay.
Yeah. All right, well, not really. Well, scalar potential is when E times D, right? And then since I also multiplied the charge of an electron, well,
No,
of course, magnitude.
generally you would define it like P dot E. I see. So I think that is the dipole. This N
Yes.
L minus 1 minus NL, that's the dipole.
Yes.
So it's the electric field, not the scalar potential.
Yeah.
Okay, thanks.
Now, so how do we make how do we demonstrate that? So first example, well, you want an isothermal process. So for example, you want it to expand. You go like that. Since the isotherm would be a vertical line, so it goes like that. So it's done by increasing the magnetic field. And then, well, once what you do is, well, you let once after some time, well, you still manipulate your magnetic field, go up to this line, and then another isotherm to compress it. So you decrease the magnetic field, and once you reach at this point, allow it to go there, and then back, and then goes back. So that's one quantum heat engine cycle. Of course, it seems irreversible right now. But, well, the same thing that can happen here. For example, go up like that. And then once you reach this isoentropic line, follow, then reduce the electric field, and then reduce it even a little bit. So that's one cycle for that one. And well, when you reverse these cycles, they are their quantum refrigeration processes. So that's one thing that you can study with quantum thermodynamics, actually. Another one, another thing that you can compute is the isothermal entropic change. And the isothermal entropic change, which are these, is just the entropy when the field was off minus the entropy when the field was on. So this one for the magnetocaloric effect, this one for the electrocaloric effect. So if this one is positive, it means that this part is more than this. That's an inverse caloric effect, because what happened is that the entropy decreased when you turned on the magnetic field. But if this is negative, it means that this term is more than this. So that's a direct caloric effect, because the entropy increased when the magnetic field was turned on. The same thing, similar thing for the electric field. And well, you can compare it for magnetocaloric effect. Yes.
So basically, this is what explains the earlier question. I think.
Yeah.
What you are doing is that you had no field, and then all of a sudden you switch on the field. So this is like a quench, and as a result, this is not an adiabatic process.
Yes.
So that's why you are like, that's why delta W is no longer zero.
Yes.
You are making some transitions from one level to other levels.
Yes, that's true. Okay. So for example, here, when you have a repulsive two-particle interaction, you have more direct caloric effect for when you switch on the magnetic field, except for this particular magnetic field and for these particular set of values of constant electric field. So if you want to decrease your entropy, use this. But well, when we look at it, when the two-particle interaction is attractive, what happens is that there are more values of H and more values of E. So as more values of the temperature for which you have a positive delta S, an inverse caloric effect. Meaning that when the two-particle interaction is attractive, what happens is switching on the magnetic field decreases the entropy for that one. What about the electrocaloric effect? Actually, when it's a repulsive two-particle interaction, it's more probable that, well, switching on your electric field will be able to decrease the entropy of your system, just like this. But when you have, and just like the just like the one for the magnetocaloric effect, when it's attractive, what happens is that there are more instances for which delta ST is positive. So switching on the electric field is also for attractive interaction will help decrease your entropy. So that's it. And well, another thing that you can, this one is still a work in progress, actually, for which we can also investigate the electromagnetic profile of our system, which is the magnetization and the polarization, and so as the magnetic and electric susceptibility of our system. Actually, here is you have what we call the direct magnetoelectric effect. And when we mean that, it means that when you modulate your magnetic fields, what happens is that you cause some polarization or electrical polarization. So what happens here, if you strengthen your magnetic field, the polarization is, let's say that you maintain your system at a particular temperature. If you keep on strengthening your magnetic field, the polarization increases. So that's what happens. Or rather, the polarization tends to be more positive for this one. And then actually, when we reverse the direction of the magnetic field going here, the polarization towards the more positive region actually tends to be accelerating or faster for this one. And well, you can also make use of the electric susceptibility. So as you see here, since positive electric susceptibility, it's more prone for these particles to go to positive polarization. But well, a converse magnetoelectric effect can happen in which we use our electric field in order to cause magnetization on the other hand. And as we observe here, well, this particular, you have a part here that is more negative and a part here for which your magnetization is more positive. But to describe what really happens in the material, you can use your magnetic susceptibility. And as you see, our magnetic susceptibility is positive. So a paramagnetic phase for this one. Actually, this ongoing research on the magnetoelectric effect has opened more avenues of this of the Fermi-Hubbard model, because in fact it applies also not only to cuprates or nickelates. It can also apply to multiferroic materials such as this. And here are some experimental realizations of magnetoelectric effect.
So, okay.
Yeah.
I just wonder, what's the mechanism which is kind of useful for these applications?
What do you mean by mechanism?
Like I cannot imagine, like, so you, let's say, tune some electric field and then you change polarization. I don't get intuition for how is it useful. Can you maybe explain that?
Actually, it's used, for example, for this one, tissue for engineering of tissues.
But
and
why
even for sensors?
Why would you want to change the polarization?
Well, that's something that the experimentalist can more of explain for this one.
I see.
Yeah.
The more polar it will mas papasok na sa cell.
Yes, where the more polarization, or rather the polarization dictates for example, I love having my wife here actually with me. So, for example, in tissue and cell stimulation, the polarity, for example, this one, tells which for example, this one is more negative. So, and this one is more positive. Tells you which part of the cell, let's say, a particular ion can enter into. So it's more of a biophysics stuff. For that, or the realization for that one is a bit of more biophysics.
But that is when you measure the polarization of the tissue, or this, because here you are talking about the sensor, right?
Yeah.
So how is the changing electric field or magnetic field within the sensor tell you something new?
So that's something that I haven't thought of right now. Lately, yeah.
I also wonder what will be application of that white blob. I don't know, maybe next slide.
Yeah. This
one is kind of interesting, right? But I'm not sure what to think about it.
This one, it says that for this particular region,
yeah,
it's more well, the susceptibility is very high for this one. So actually, in general, if you see the whole graph, the magnetic susceptibility is positive everywhere. So it indicates that the materials actually paramagnetic material, right?
But can you say that's the region where the sensor is the most precise?
That's one implication. That can be one implication. Yeah.
Okay.
Yeah. Yes, question.
So you just mentioned that these were useful for cuprate materials or multiferroic materials.
Yeah. And multiferroic, yes.
Yeah. So did you compare this with actual experimental data, and how do they look? And how?
Not yet, actually.
I see. It will be very interesting to know whether this very simple system that you have. I mean, it's not a very big system.
Yeah.
But by simple, I mean that, like, it's a small system.
Yeah.
So you can control more or less all the things, all the components.
Yes.
And if it can faithfully reproduce the experimental data, yes, that will be quite interesting.
Yes, exactly. Yeah.
Okay. So have you checked it or not yet?
Not yet. Actually, yes. Okay. Thank you for that. That's a very interesting thing actually to check. Now, so yeah. So actually, that's a bit almost everything for the quantum thermodynamics. I'll now go to spin transport. And this one has a more, compared to a while ago, for which I used exact diagonalization. This one, I will make use of more analytical methods. Because, well, if you recall, of course, you have your ye old Ohm's law. But at the same time, if you put in quantum into the perspective of your current, it just tells that, well, in fact, your current can be divided into two parts, a paramagnetic part and a diamagnetic part. And well, that tells that, and well, because of that, not only charges can flow among your quantum systems, your charges can flow, meaning electrical current. Energy can also flow, meaning a thermal current. And even magnetic moments can flow, spin current. Actually, this is the trend of technology also nowadays because they are drifting from electronics to even spintronics, right? And then came all the tronics that there are, tristronics, valleytronics, etc. That are being used to in order to make the transfer of not just information but even to increase the efficiency of our tools nowadays more lossless. And actually, this is a rough picture of spin transport. And in fact, when we mean spin transport, not the charge itself is not necessarily the one that's being transported. It's the spin. It's the spin of the particle that can be transported. For example, this spin up, and let's say that this is a non-spinful region. This can go there, then forward, then usually this is made up of nowadays these are realized more in experiments by alternating magnetic and non-magnetic regions. So a rough picture of our spin current expression is actually given by equation number 18, for which this is again your tunneling, your nearest neighbor tunneling energy, spin of the particle. And by the way, well, if it's for this index, it's either up or down. But for this part of the summation, it's +1 if spin up and this is delta x as well. It is the width of your lattice site. And then Q is, well, the momentum mode. And then RLX is the location of the Lth lattice site. Okay. And well, in fact, if you have a high temperature, you can no longer distinguish if it's the spins or the charges that are being transported. So actually, there are some papers nowadays by more of, if I'm not wrong, they are, what's this? Slovenians, actually. They're authored by Martin Ulaga et al. They have a bunch of papers dedicated to this one. That compares the charge and the spin current. But let's focus ourselves on the spin conductivity of the part of the system. In fact, you can compute for the spin conductivity by making use of what you call the Kubo formula, when as the Hubbard model is actually obedient to linear response theory. So that's why we can make use of this. So here are some terms that you can get here. Eta and nu are the dimensions, so x or y or z. And since it's one-dimensional, x only for this one. And actually, you can compute for your current correlation first in order to get this, and then you have to take the real part of that conductivity. Actually, there's a missing term here. There should be an imaginary part of this one because of the I over there. Now, here are some results. So actually, this will involve, if you see a while ago this, if you plug into this, you would have to compute for your nested time-ordered products. And so make use of Wick's theorem. And then from that one, you will be able to get Green's functions. And then from the Green's functions, you would be able to get an analytical expression for the real part of the spin conductivity. And well, run the simulations. So once you run the simulations, here are some results. Well, if your two-particle interaction is repulsive, what it shows is that, of course, low temperature, no transport. As expected, because when the temperature is equal to 0, according to, absolute 0, your all motions stop. So we have to expect that 0 current, zero spin conductivity at 0 temperature. But what happens is that it goes 0, then after a part, let's say for example, U sub 0 equals to, it peaks over here. Actually, if you zoom in a bit, it fluctuates a little and then goes down as the temperature increases for repulsive two-particle interaction. And actually, that's not necessary. In fact, the stronger this two-particle interaction is, the higher the temperature the peak takes place at. However, higher two-particle interaction does not mean higher spin conductivity. Because, for example, look at this one. This is 16, this is 8. So, yes, it achieved a greater peak for that one. But, well, when the two-particle interaction is attractive, what happens is that, as you see here, 0, and even if you compare the scales, that's 10 to the negative 8. This one is 10 to the negative 30. As expected, because attractive two-particle interaction. Let's say that, for example, a spin up was trapped here. Since there's an attractive two-particle interaction here, it does not want this spin to go this way. If it's repulsive, this one wants to repel it, transport it that way. But if it's attractive two-particle interaction, this spin down does not want to let go of this spin up to go there. That's why you need. That's why there is a need for temperature to aid that spin transport. Okay. Now, in fact, your external electromagnetic fields have an effect on your spin conductivity. And let's start with the more boring case, which is attractive two-particle interaction. In fact, what happens is, well, I did not put all the graphs here, just the ones to sample it. But if you put an external magnet, by the way, the one a while ago is no external fields yet for these ones. But if you have external magnetic fields and external electric fields, what happens is that they approach a uniform behavior at these temperatures. So that's pretty it. So it makes, there is an optimum behavior for your spin conductivity for attractive two-particle interactions. But let's go to the repulsive case. So if you zoom in a bit here, well, this red line here is H equals 0.5 times T. And this blue line over here is H equals 2T. So the stronger the magnetic dipole, the stronger the magnetic field is, the higher the spin conductivity. And it's expected. Why? Because, for example, since you have a half-filled lattice a while ago, right? When your magnetic field points, for example, downward, it forces all the lattice, all the spins in the lattice already populating the lattice to point down. So when a spin up wants to move through it, okay, free space over here and free space over there, free space, so it can move. It can move easily. And as for what about for the electric field? Actually, for the electric field, if it's more positive here, if it's greater, well, higher spin conductivity, as expected as well, because, well, let's say that your for example, these are electrons, and electrons, right, are electrons, for example, are what? Electrons, for example, are going in the other direction as your positive electric field. So let's say that, well, your electric field points here and it gets stronger. So more force to push it that way. So the results are just the results are more sound on this one.
You have about 10 minutes.
Yeah, and this actually is the conclusions already. So for the conclusions, so we see that, well, when we have the for repulsive systems, we see that your magnetocaloric effect increases your entropy, while the electrocaloric effect helps decrease your entropy. And, well, but if it's a repulsive, an attractive two-particle interaction, either is preferable if you want to decrease your entropy. And then actually, the net positive charge, there's more net positive charge density from the direct magnetoelectric effect. And paramagnetism in the system is observed because of the converse magnetoelectric effect. However, for spin transport, as expected, our spins should freeze at temperature approaching zero. And at low temperature, there is a peak of your spin conductivity for repulsive interaction, yet an increasing behavior for attractive interaction. In fact, when your two-particle interaction is positive, if you want to increase your spin conductivity, you just have to have a finite magnetic field and a more positive electric field. But well, if it's an unattractive two-particle interaction just like this, turning on your external electromagnetic field would just allow your spin conductivity to approach a uniform behavior. So actually, just for future direction of this, so this research is still ongoing. In fact, you can look at a lot of things like charge and thermal transport, and even some more thermodynamics, just like this one, thermodynamic uncertainty relations, for which I'm most interested right now. And that's why I came to Dr. Shafranek here. And well, we can add next nearest neighbor interactions, more bath levels, and even look at things like spin-Seebeck effect. As Richard Feynman has told, there's plenty of room at the bottom. So these are my references. And well, if you want a copy of this, you can just scan the QR code here or insert this, or rather type this link. Maraming salamat po, hanggang sa hap nila.
Thank you. So we have some time for the questions.
I will ask a question.
Yeah, sure.
About the detail. So when it's again about I'm interested in the the Hamiltonian that you look at. So you consider how many wells? Like 2 wells
for
and 2 particles?
For which one? For the
magnetocaloric effect?
For magnetocaloric effect is half filled. So maximum 1 particle per site. So in average.
Yeah, so 2 well, 2 particles.
2 well, 2 particles, yes.
And for spin transport, what is the situation?
Well, I let the number of sites approach infinity, actually. Okay. It can be a very long one because once you derive once you do the analytical expressions, there will just be a particular expression that will approach 1. Or there will be a part of the expression that will just approach 1 when you have infinitely many sites.
I see. So there you don't use your, what is the expression that you were plotting there? Could you show?
Which?
For spin transport.
For spin transport. Actually, I was plotting this, the real part.
But this pi, this you have to calculate numerically, no?
I have to first calculate it analytically by inserting this one. Since you have right second quantized operators here, and if you insert it, well, you will have nested, let's go back first. There are 2 for the spin current, right? And then when you insert here, so spin current, 4. So you're going to make use of Fick's theorem actually to evaluate. Well, since 4 by 4, you cannot immediately do this, right? And then, well, if you use many particle physics, you're going to make use of Fick's theorem in order for these time-ordered averages be 2 particle in terms of 2 particles, or in terms of 2 operators, I mean. Yeah. Then from that you get the Green's function.
Yeah. So here, where does that information that you have 2 particles and
not 2 particles, 2 operators. Actually, for this one, I still make use of the half-filled model, and the half-filled is done by the half-filling is done by.
Half-filling goes into the Hamiltonian.
Yes.
And the value of mu you take half.
There, yes. Okay. Actually, another thing that you can explore here, since you have a bath already, right? Well, this one, if you make it, this one is put in an ideal condition that you control the system in such a way that you fix it. But another question that I have in mind is that if you have a bath already, can you really fix the chemical potential? That's another direction that I have in mind actually for this one. There are a lot of, actually it's all directions.
For spin transport, what you are doing at the moment is that you are working with linear response theory.
Yes.
And in linear response, the bath is weakly coupled, so
yeah,
it's fine.
Yes.
But if you want to look at this question, then you will have to look at the full system plus bath plus interaction Hamiltonian, and then you are back to doing exact diagonalization again.
Yeah.
So probably you will not be able to look at a very big system.
Yes.
And then it doesn't make sense to talk about transport, like just two sides.
Well, this one is not two sides.
No, I know, because you can do it analytically.
Yeah, but to do numerically.
But if you just look at it like, by doing exact diagonalization with two sides, then
that's hard.
Yeah.
If you, especially adding more sites, that will make your laptop crash. Yeah.
Any other questions? All right, then let's thank the speaker again.
Let's have a picture. Yeah. Where's the title slide? Yeah, I should have put the title slide at the end. There it is. That was me 3 years ago. 5 head, but now it's, if you measure, it's now 6 fingers, so 6 head. That can happen to you. Now let's have a picture, guys. Can we ask to take our picture? No, I think we can ask someone to take a picture for us. But does anybody know how to stop the recording? Yeah.
We have to ask.
I think we have to ask the page that we need tech support right now.
Yeah.
Yeah.
Oh my God. He's going here. Whenever he wants to get a visa, it's like. So Rohit went to get his visa. And apparently tomorrow is the impeachment day.
Yes, I don't know.
Yes.
False president. So last time when Rohit went to get a visa, there was a coup, and then he didn't get his visa for a long time. So. Yeah.
Wow.
Oh, it was the recording?
Can I end this?